Okay, so our learning targets today. So we've been dealing with polynomial functions, linear functions. Well, today we're going to make a switch, a turn, and we're going to talk about rational functions. Okay, we're going to talk about end behavior of rational functions and then zeros of rational functions. And we're also going to solve some rational inequalities. So that's probably going to be brand new. I can't remember how much you guys do with rational functions in Algebra 2, but I don't think it's a whole lot. Okay, I think it's just a little bit here and there. So that's what we're going to look at today. Okay, well, if we're going to talk about a rational function, we need to know what it is. All right, and a rational function basically is the quotient of two polynomial functions. You'll also hear me refer to it as an algebraic fraction. Okay, so you'll see it written like this: R of x equals f of x over g of x. We've got two polynomial functions. The only thing, that bottom function cannot equal 0. Okay, what happens when that bottom function is 0? Yeah, it's undefined, right? Your paper explodes. All right, have I told y'all that story? When I first started teaching, basically education classes do nothing to prepare you for what it's really like to teach, right? But I believed in doing all the things that they told us to do, and so that was back when I graded homework before I realized that was a farce. But anyway, so if they didn't have their homework, they had to fill out this little pink slip about why they didn't have their homework, and after so many, I would, email their parents or whatever, okay? So as you can imagine, that got exhausting over time. And I had this one little kid, God love him, who just never did his homework, all right? And his excuses, just got more and more and more creative. And the last pink slip I ever had anybody do, and especially him, his response was, I divided by 0 and my paper exploded. Okay, so now that took a lot of creativity and some math, so I gave him 2 points on his homework. Just because of that. So, but it was the last time we did a pink slip about not doing our homework. So now I always say that if you divide by 0, your paper will explode. So don't do that. Okay. Anyway. All right. So let's take a look at some examples and let's see if we can figure out, do they represent a rational function? Are they a polynomial function divided by a polynomial function? All right. What do you think about that first one? Yes or no? F of x right there. No. All right. I don't even see a division bar. Okay. So this one is a no. All right. We can't really call it a polynomial function because it's got that fraction exponent, but it definitely is not a quotient. All right. What about h? Yeah, that one is. Okay. All right. That one actually is. People will say, well, 2 doesn't have an x with it. Okay, but our denominator is definitely a polynomial function, okay? So, and 2 could be considered a polynomial function. Now, that being the case, look at g of x. What do you think on g of x? Is it a rational function? Is it an algebraic fraction? Okay, most people will say yes, okay? But could I rewrite this? Could I rewrite it like that? Yeah, all I did is pull out that factor of 1/3. So typically we will say this one is a no, okay? If I have a constant in the denominator, then we say that it's just a polynomial function because I could pull that constant out as a fraction, okay? So only if the constant is in the numerator do we say that it is indeed a rational function, okay? So just wanted you to see the difference between those two things, all right? Now, let's talk about end behavior on a rational function, okay? End behavior on a rational function is not as simple as end behavior on a polynomial function because I no longer have just one polynomial function. I got how many? I got two. Okay? So here's what we do. All right? End behavior of a rational function is affected by the degree of each polynomial and their leading coefficient. Okay, so I can no longer just look at one thing. Okay, I've got to look at both and think about kind of how they play together. Okay. All right, well, how does that work? Okay, how does that work? So basically what's going to happen is the polynomial with the greater degree, all right? So with the greater degree, we'll have what we call input values. That would be x's. That dominate, I love that word, dominate the entire function. Okay, and then it dictates the end behavior. Okay, so the polynomial with the greater degree, he's the boss. He dominates and dictates. Okay. Right. There are going to be three situations that could happen. Okay, sorry, I just got choked on my own spit or something. Right? So case 1, case 2, case 3. Okay? And each case is going to give me something a little bit different. Okay? So the degree of each polynomial and their leading coefficients, bless you, have an impact on our end behavior. And the polynomial with the greater degree, right, will dominate the entire function and dictate the end behavior. Okay, so let's walk through the three cases. All right, let's walk through the three cases. And then we're going to look at some examples, okay? So don't panic. We're going to look at what all this means so you're not freaking out. Okay? So case 1, the degree of the numerator equals the degree of the denominator. Okay? When that happens, our end behavior will approach the horizontal asymptote. It's going to create a horizontal asymptote. Okay, well, how do I find that? It is just the ratio of the leading coefficients. Okay, so if the degree of my numerator equals the degree of my denominator, my end behavior, both directions, that limit that we do, will always approach that horizontal asymptote, which is the ratio of the leading coefficients. Okay. Okay, so let's say that's what we have. Okay. 5x cubed plus 2 over 6x cubed minus 1. That's my rational function. The numerator, the degree, equals the degree of the denominator, okay? They're both cubic, all right? So I'm going to look at the leading coefficients. What's their ratio going to be? 5 over 6, okay? So my end behavior would be this. The limit as x approaches negative infinity, we're just going to call that f of x, would equal 5 over 6. The limit as x approaches positive infinity of f of x would be 5/6. It's going to approach my asymptote. All right, that's a horizontal asymptote. That ratio of those two leading coefficients only when the numerator equals the denominator, okay, in terms of its degree. All right, case 2. All right. The degree of the denominator is greater than the degree of the numerator. Okay. When that happens, our end behavior will approach always 0. Okay. And the reason it does that is we get a horizontal asymptote there. We're going to talk more about asymptotes here in just a second. Okay, we'll approach 0 because I have a horizontal asymptote. At 0. Okay. So if the bottom's bigger than the top, right, our end behavior will always approach 0. Okay. Oh, it's music. It took me a minute. Yeah. Okay. All right, so let's look at this one. I have 2x squared minus 7 over 4x cubed minus 1. Okay. Notice the denominator is a cubic. The numerator is a quadratic. Okay. So anytime that happens, right, I don't care about anything else. All right. The end behavior, both are going to approach 0. Limit as x approaches negative infinity of the function, limit as x approaches positive infinity is 0. And we're going to look at some graphs here in a second so you feel that a little bit better. Yep, there's always one. Break of the toys. I know that was one of the first ones to break. The squishy balls the stress balls, they ruptured those quickly first semester. Okay, all right. So if our 2 degrees can be equal, the bottom can be bigger than the top. Guess what? The top can be bigger than the bottom. Those are our 3 things that could happen, okay? So if the degree of the numerator is greater than the degree of the denominator, here's the cool thing. The end behavior will mirror the polynomial of the resulting quotient. Okay, so the end behavior will mirror the polynomial of the resulting quotient. Let's look at one of those. Okay, so let's take a look at that function. 4x cubed minus 1 over 2x squared minus 7. So I just flipped them. All right. Notice this time the higher degree is on the top. Okay. So here's what we're going to do. We're going to take those 2 degrees. All right. And I'm going to do some imaginary simplification. X cubed over x squared. What would that reduce to? X. Okay. So the end behavior of that entire big nasty function is the same as the end behavior of that nice little neat little function, okay? What is my end behavior for just y equals x? Okay, so the limit as x approaches negative infinity and the limit as x approaches positive infinity, okay? What does the line y equals x look like? Right? It's up on the right, down on the left, so it looks like this. So talk about my end behavior. What's it doing on the left-hand side? It's negative infinity because it's going down. And what's it doing on the right-hand side? Positive infinity because it's going up. Okay? So that's what I mean by it follows the behavior of the quotient. Right? So we simplify those 2 leading degrees, all right, those 2 leading terms. And whatever I get, that's what my end behavior is going to be. It's going to match it, okay? So, end behavior is important. That's where we write the limit statements, okay? Now, on the top of the next page, I'm going to add a little something above where it says slant asymptote. But one of the things about rational functions is we get lots of asymptotes, okay? We get vertical asymptotes. Which way does a vertical asymptote go? Up and down. We get horizontal asymptotes. Which way does horizontal go? And then we also get something known as a slant or an oblique asymptote. You want to guess what that one does? Yeah, it's got some slope to it, okay? So I think it's a good name, slant. Makes sense, right? So what I want us to do is we're going to talk through all these different characteristics, all right? But up here at the top, let's write a little bit about horizontal asymptotes. Okay. Okay. Horizontal asymptotes always have the equation y equals, okay? So you can't just put the horizontal asymptotes 4. Nope, you got to put y equals 4, all right? It's very specific. It's an equation. It's a linear equation. So it's always going to be y equals, okay? Y equals, and you'll have a number, all right? The times when it happens, okay? It happens with case 1, all right, that we just talked about on the other side, because it would be a divided by b. It's going to be my 2 leading coefficients divided. When my degrees match, it's just my 2 leading coefficients divided. And it happens with case 2, okay? If I have the larger degree on the bottom, it's always y equals 0. So those are the only 2 times that we're going to get a horizontal asymptote, okay? If my degrees match, it's the ratio of my leading coefficients. If the bigger degree is on the bottom, it's always 0. Okay, always. So a horizontal asymptote, y equals, and it'll be some number. Now, a slant asymptote only occurs occasionally. It does not occur all the time, all right? And it cannot occur in conjunction with a horizontal. So you're either horizontal or slant, but you can't be both, okay? You could be neither, but you can't be both, all right? A slant asymptote only happens when the numerator is exactly 1 degree larger than the denominator. Okay, so it only happens when the numerator is 1 degree larger than the denominator, all right? We'll talk about how to find it in a couple of days. All right, right now we just need to know if it exists, all right? And then make you a note over here, all right? Can't have both horizontal and slant. Okay, they are independent of each other. Or I guess they're dependent on each other, I guess is the best way to say that. Okay. So all we need to be able to do today when it comes to asymptotes and end behavior, all right? Can we figure out what kind of asymptotes we have? All right, if I've got horizontal ones, let's write their equations, all right? And then can we do end behavior, all right, for a rational function? So that's our first kind of big chunk of what we're doing, or actually it's both, okay, of those things. So let's take a look, all right, at these examples. Let's look at the first one. So I have f of x equals 3x squared plus 4x minus 7, 5x squared minus 3. It wants me to figure out, do I have a horizontal, slant, or neither? Okay, because it's got to be, those are my options. If it's horizontal asymptote, we want to write the equation of that asymptote. Okay, so we're just trying to figure out the asymptote. So we're going to check those highest degree terms. All right, so let's look at the first one. If I highlight those highest degree terms, I have a 3x squared and a 5x squared. Okay, we check, are the degrees equal or is one bigger than the other? Okay, which one do we have there? They're equal. When they are equal, then we have a horizontal asymptote. Okay, y equals, we will always state y equals, and then we just take those leading coefficients, 3 and 5. We reduce if we can, and that's my horizontal asymptote. Okay, so that's all we do is we look at the highest degree terms. Okay, so we're checking those three cases. All right, let's look at the second one. Okay, looking at those highest degree terms. So I have a 2x and an x squared. Are they equal? No, so it's definitely not the first one. Okay, who's bigger, top or bottom? Bottom. If the bottom's bigger, it's a horizontal asymptote. Y equals 0 always. Okay, if the bottom degree is bigger, it's always y equals 0. Okay. All right, and then let's look at that last one. Okay. So we've got g of x equals 2x squared minus 4 and 5x plus 9. Highest degree terms, top and bottom. Okay. Question 1, are they equal? No. Where's the bigger one, top or bottom? Top. And if that happens, okay, it's not horizontal. All right. The next thing we have to check is it the slant asymptote? If it's slant, the top is 1 degree higher than the bottom. Okay. Is that what we've got going on? Yes. 2x squared is 1 degree higher than 5x, so this one has a slant asymptote. It doesn't ask me to find it, it just wants to know if I got it. Okay, so that's all you'll have to do today. We'll find it in a day or two. Question about that. It's just knowing the rules, all right, for that, kind of the cases and what are my options, what could happen. Okay, so now let's take it one step farther with these next examples, okay, because the asymptotes help me to know the end behavior, okay. So this time we're going to write our 2 limit statements for our end behavior. So let's look at that first one together. All right, then I'm going to let y'all practice these next ones. Okay. So on A, I've got f of x equals 2x cubed and some stuff over 6x cubed and some stuff. So still, we're looking at those highest degree terms. So I have 2x cubed and 6x cubed. All right. Is it going to have a horizontal asymptote? Yes. Okay. They're equal, so what would my horizontal asymptote be? 1/3, 2 over 6, which would be 1/3. Okay, you always want to reduce it, all right? If I have a horizontal asymptote, my end behavior is the asymptote, always, okay? So, limit as x approaches negative infinity of f of x would equal 1/3. Limit as x approaches positive infinity of f of x would be 1/3. Okay? All right, so take a second, see if you can do those next 4. 2 are equations, 2 are graphs. All right? Our end behavior, writing those limit statements. Did you feel better once you did your test corrections yesterday? Or no? Yes, no, maybe? A little bit, okay. I'll get those graded ASAP for you. Oh. I can't wait till I can eat fruit again. I love fruit. Every time you're over there eating it, I'm like, It is so great. And do y'all know, this is crazy, you probably don't care, but anyway, it's probably been 15 years. I've only been eating fruit for about 15 years, which sounds crazy, but it was just something I never really liked. And then all of a sudden, I don't know, like grapes tasted like, reminded me of eyeballs. Like, you know what I'm saying? Like, you know how you have these weird things? So that was my weird thing. And I didn't eat fruit. And then all of a sudden, I just picked up fruit and then, so good. But now I can't have it right now just because the sugar, the natural sugar content in it. So until I've lost 75% of the weight I want to lose. So I'm living for the day. Your girl can have a strawberry and a blueberry and oh, I can't wait for all the berries. Okay. It's a pineapple. Oh, I love pineapple. Pineapple on pizza? Yes. I'm a yes for pineapple on pizza. You're a no, Wilmer. It's okay. You just haven't got a sophisticated yet. You will. Okay. It will come with time.
It's good. The way you
The 5-0 pizza from Fairview is my favorite. Have y'all had that one? It's ham, pineapple, banana peppers, and maybe bacon. I don't know. It's got pineapple on it though, and like there's some kind of hot honey drizzle. Oh, shut the front door. It's so good. Anyway.
Charles, I don't know what it is, what it's called, but on Indian Lake, the pizza place over there, they have pretty good pizza.
Do they? I'm making barbecue chicken in my crock pot today, and one of my favorite things is like Friday, I'll make myself a barbecue chicken pizza with it. Can't wait. I make it on the egg white tortilla thing. It's so good.
Oh, I didn't do it. I'm trying to figure out what will be zero.
Did he say he didn't do it? We need to whoop him. He's too busy worrying about pizza.
Exactly. I got to work. Get to work though for the week. Will it be zero? Yeah. Okay.
Okay. Okay. Yeah, Caleb over there eating all of his fruit. Don't spit it on the floor. Okay. Now we're all looking at him. That's embarrassing. Do not choke. I don't have time to do the Heimlich today. I'm too tired, nor do I want to fill out the paperwork.
Okay. I think I know what to do. Go back up.
Do y'all eat Brussels sprouts? Only in my adulthood have I learned to eat Brussels sprouts, and they're so good. Cabbage. Oh, yes. Boiled cabbage. Mashed potatoes, fried chicken, boiled cabbage. Yes. Yes.
It depends on the mix.
Okay, but you got to put a little bit of sugar in it and some hot pepper. That's what makes it good. Sorry.
Wait, what?
Your girl loves to eat. I love it. Okay.
The degree is more higher. Gotta get that when the top degree is this bottom. No. You do this over that, and then it simplifies to x. And then x
Yes, ma'am.
is like. So then that's the end behavior for that because it simplifies to x. So I think it's negative infinity to positive. And that's the way it's
All right, let's double check these and see how we did. Okay.
X. X is just.
All right, so if we look at B, all right, I got a 5x squared over a 2x cubed. Are we going to get a horizontal asymptote? Okay. Are we going to get a horizontal asymptote? Yeah, we are. Okay. They're not equal, but the denominator's bigger. When the denominator's bigger, what's my asymptote? 0. Okay. Which means my end behavior is approaching 0. Okay. Both sides. Okay. So denominator was bigger than numerator. Okay. Let's check the third one. All right. So I get h of x equals negative 3x to the fourth over x cubed. Is there going to be a horizontal asymptote on this one? No. Okay. The top's bigger. So what we need to do is to simplify that. Okay. Because I got to know which function is actually dominating or what it would be. Okay. So negative 3x to the fourth divided by x cubed, what would that reduce to? Negative 3x, okay? That's a linear function. What does it look like if I graph negative 3x? Yeah, it's got negative slope, so it's going to look like this, okay? So when that happens, my end behavior matches the end behavior of that quotient. So the limit as x approaches negative infinity of, this is h of x, all right? Which way does it point on the left? On the left, it points up, right? Because I've got negative slope. And then on the right, the limit as x approaches positive infinity of f of x would be negative infinity. So take a second and dig that one especially, okay? When I don't have a horizontal asymptote, we do have to divide and reduce, okay? Our end behavior becomes the end behavior of that quotient, what happened when I divided, all right? Question on those three. Those are our equation ones. Those are the ones you're going to see the most, okay? Now it gave me two graphs, which I like. We've not really looked at a rational graph yet. So they do funny things, okay? They have asymptotes, vertical, horizontal, like crazy things going on. So we're talking about end behavior. What's it doing on the far left? What's it doing on the far right? Okay, so if I look at this left-hand side, so I'm talking about the limit as x approaches negative infinity. All right, we're going to call it f of x. Okay, so on this left-hand side, what's it getting really close to? Yeah, it's getting really close to that asymptote, which is 2. Okay, would you let Elise back in? Thank you, baby. And then if we do the right side, the limit as x approaches positive infinity of f of x. Okay, so on this right-hand side, what's it getting really close to? 2. Okay, so it's approaching that horizontal asymptote. Okay. All right, and then for that last one, so limit as x approaches negative infinity of f of x, limit as x approaches positive infinity of f of x. Okay. What are they doing, or what's it getting close to on the left? -1, and on the right, -1. Okay, so it's getting close to those asymptotes. Questions about that? Okay, in behavior, asymptotes. If it asks you for asymptotes, you're writing the equation. If it asks you for in behavior, you're writing the limits. Okay, where we need the asymptote. All right, so that we can know we did it right. Head chill. Okay, question on that. All right. Oh, $1.49 4-piece mozzarella sticks at Sonic today. Just got the advertisement. $1.49.
Oh, 29 pieces of mozzarella sticks.
No, for 4 pieces of mozzarella sticks. You would take that? I love mozzarella sticks, I ain't gonna lie. All right, so let's talk about zeros, okay? Doing zeros of polynomial functions was really easy. We factored, we set each factor equal to 0, okay? But now I've got 2 polynomials and there's junk going on, right? Because we're dividing. So when we talk about zeros of rational functions, let me ask you a question. If I have a fraction and I want it to equal 0, what part of my fraction has to be 0? The top, the numerator, okay? Because if the denominator is 0, what happens? Your paper explodes, okay? We ain't got time for that because we're using tablets. All right, that could get real messy. All right, so zeros of our functions, they are where the numerator equals 0 as long as the numerator and denominator do not share a factor. Okay, something else happens when they share a factor. It's not a 0. So for today, we're not going to consider those. Okay, so if I have an x plus 2 on the top and an x plus 2 on the bottom, okay, we won't consider that for a 0. All right, we'll mark it out. Okay. So we're looking at just the numerator, where the numerator is equal to 0 as long as we don't have shared factors. So that means we're going to have to factor if it's not done for me. Okay. So we're going to have to do some factoring today, but that's okay. Right. So where the numerator is equal to 0, as long as they don't share a factor. Cotton candy margarita is good. It's just margarita flavor. It's not real margarita. First block goes, having a bad day? And I'm like, no, it's just the flavor. Okay, it's a little packet. So good. Okay. So let's look at these first two. Okay, so I have the first one, 2x cubed over x squared minus 4x minus 45. The first thing I'm going to do is think about factoring because I got to make sure that I don't have matching factors. Okay, will that numerator factor? Is there anything we could pull out? Nah, we're just going to leave it 2x minus 3. Okay. My denominator is a trinomial. If I'm lucky, I might be able to do something with that. Okay. Do I have numbers that multiply to 45 and add to 4? Yep. 9 and 5. Minus 9 plus 5. So do we share anything in the numerator and denominator this time? No. Okay. So for zeros, the only part I'm going to consider is the numerator because they didn't share anything. So 2x minus 3, I'm going to set it equal to 0. 2x would equal 3, so my only 0 is 3 over 2. Remember, a 0 is the same thing as an x-intercept. All right, let's look at that next one. So I have j of x is equal to x squared minus 4 over x squared minus x minus 6. Okay? Can I factor that numerator? Yeah, what's it going to factor into? X plus 2x minus 2. It's a difference of two perfect squares. Right? The denominator is a trinomial. All right, so we want to multiply to negative 6 but add to negative 1. I think that one's going to work too. Plus 2 minus 3. Okay. Do they share a factor, numerator, denominator? Yep, so I'm gonna mark that one out and not worry about it. I can't consider that for a 0 because it matches from top to bottom, okay? It's something special in the graph, but we're not ready to talk about that yet, okay? So the only thing we're gonna consider are those non-repeated factors that are in the numerator, okay? So my only 0, x minus 2 equals 0, so my x-intercept is at positive 2. Okay. Question about that? We good? Okay, zeros come from the numerator. All right. So now I want us to jump into the difficult part, okay? And not that it's difficult, it's just tedious. We have to be very careful, organized with our thinking, okay? So we're going to actually talk about solving rational inequalities, all right? And if you look, I've given you some steps, all right, or some things to think about. Notice it says a bit more involved. You think? All right? There's a lot of stuff we have to think about when we solve a rational inequality, okay? When I have that algebraic fraction is greater than or less than something, okay? So there's just a lot more involved, all right? So here's what we're going to do, okay? One of the things we have to do is to make sure that the inequality has 0 on the other side. So we want all of our numbers, expressions, everything on one side, 0 on the other, okay? We also want to make sure that we have a single rational function. We don't want to have something like 2 plus x minus 1 over x plus 4, okay? That's a no-go, all right? I want it all together as one function, all right? So we don't want that. We're going to set the numerator and the denominator equal to 0 this time, and that's different, okay? Those are going to be important numbers that we need, okay? So this is different. It's not just zeros. It's numerator and denominator, okay? And then we're going to make what's called a sign chart. And now we'll use these in calculus, but what a sign chart does is it tells me between certain values, all right, x values, is my function positive or negative, all right? And how we'll test that is we'll just plug in some values that I can work with, okay? Now, we want to be careful to mark, and this is important, to mark the values where h of x is equal to 0 so that we never include those values in our solution, because those are those undefined spots, okay? They're undefined spots, so we want to be sure that we note those so that I don't ever put a bracket on that, okay? Because I cannot equal that number. And then we're going to test some values within each interval to see if the function's, I don't want to write with a highlighter, if the function is positive or negative, right? Then we'll interpret our sign chart. So there's a lot to think about here, okay? After we've done 1 or 2, I think you'll see it. It won't be that big an issue, okay? But the first few are going to be tough, all right? They're going to be tough. So I want to walk through these. I've got several examples of these for us to do, okay? Because these are the most involved. This is the hardest part about what we're going to do today, okay? And something I know you've never seen. Yay! Okay, I like it when I get to teach you something for the first time. Okay, it's like you have this blank tapestry in your head and I get to put all the things on it. Okay, here we go. All right. So we're going to start with this first one. X minus 2 divided by x plus 6 over x minus 3, the whole thing greater than or equal to 0. Okay. So if I take that rational function and I graph it, I want to know where's all the parts that are above the x-axis. Okay. Now, this would be on a non-calculator section. Okay, so you're not going to have the graph to plug in and see. All right, we're going to have to do the math. So here's the first thing we're going to do. We're going to take the numerator and set it equal to 0. And we're going to get some special values. Okay, if I set the numerator equal to 0, what x value would I get up there? 2. Okay, we're going to do the same thing with the denominator. Okay, how many special values would I get down there? 2. The first one would be -6, and the second one would be +3. Okay, so is everybody good on what I did right there? Okay, I just found both places where it would equal 0. Okay, step 2 is we're going to do this sign chart, and it looks a lot like a number line. Okay, it looks like a number line, and what I'm going to do is I'm going to put those special x values on that number line in order. All right, so I have a -6, a +2, and a +3. Okay. Now, remember when it says note the ones that came from the bottom? Here's what I'm going to do. I always put parentheses around those ones that came from the bottom so that if I ever have to use that number in my answer, I put a parenthesis at that number, okay? Those are where my paper would explode, and we don't want that, okay? So we're going to use parentheses for when we write our answer. All right. Everybody with me so far? Okay. Now, this is where we do some arithmetic in our head. God bless America, okay? So what I'm going to do is I'm going to pick some x values between these numbers and outside of them, all right? And I'm going to plug them into this original function to figure out, is my function positive or negative there, okay? That's all we're going to do is figure out where it's positive or negative, okay? So give me a number that would be smaller than -6. -7, okay? So here's what I'm going to do. If I plug in a -7, now I'm not going to always write these down, all right? But I'm going to do it for your example so you have it in your notes, okay? So I'm going to start with a -7. If I plug a -7 in on the top, would I get a positive or a negative number? A negative, okay? On the bottom, -7 plus 6, what would that give me? Negative. And -7 minus 3. Negative. Now, I want you to think about what we're doing. We're taking a negative divided by a negative times a negative. So simplify. What's a negative times a negative? And a negative divided by a positive is a negative. Okay? And I just put the sign there. Okay? If I did all the arithmetic, would I get a positive or a negative? All right? Remember, we're multiplying in the denominator. Okay? Give me a nice number between -6 and 2. Zero. All right, let's do 0. Okay, 0 is between -6 and +2, but you could do -1. Okay, but I'm going to use 0. All right, if I plug 0 in at the top, 0 minus 2 would give me a negative. On the bottom, 0 plus 6, that would be a positive. 0 minus 3, that would be a negative. Now let's think about what the overall sign would be. Okay? In the bottom, a positive times a negative is a negative divided by a negative is a good. Oh, see, y'all can't do arithmetic. Yay. Okay? We're just doing signs. All right? Everybody following what I'm doing? Okay. We got to do it 2 more times. That's the bad news. All right? Number between 2 and 3, that's not real easy. Okay, so we just got to say, all right, let's do 2.5. Okay, it's 2.5. It's in the middle, but I think we can still make it work. Okay, because we're just looking at signs, not actual answers. Right? On the top, 2.5 minus 2, would that be positive or negative? Positive. Okay, 2.5 plus 6. 2.5 minus 3, negative. Okay. What's that whole fraction sign going to be when you're done? Negative. Okay. And then let's do one more. So all this stuff I'm writing in green, you don't have to write all that down. You can do it in your head. Okay? But the sign chart is good. That way it keeps you honest with your answer. Okay? Now, let's plug in 4. 4 minus 2. 4 plus 6. 4 minus 3. All of those positives give me a okay. All right. So now we filled in the sign chart. All right. Now we have to answer the question. Where is this greater than 0? Which parts of the chart do you think represent greater than 0? The positive parts. Okay, the positive parts. So I'm going to look at those parts. I'm positive here, and I'm positive here. Okay? So positive is greater than 0, negative is less than 0. So now we're going to write our answer. All right, we've done all this work, and now we're ready to write our answer to solve this inequality. Okay? The first place I highlighted was between -6 and +2. So -6 has a parenthesis on it. I'm going to use a parenthesis. 2 does not, guess what I put on it? A bracket. Okay. And then I've got one more spot. All right. The next spot, all right, it starts at 3. And then it follows the arrow to the right. So what would I use? infinity. Okay, and that's my solution to that inequality. Okay, do you see what I mean by tedious? It's not that it's hard, it's tedious. All right, there's lots of little bitty things we got to remember. Right? Whew. All right, to quote my nieces, let's do the another one. Okay, it was never another, it was always the another. All right. All right. Okay, so let's look at this one. Is there a possibility that I could factor? Yes, they didn't do it for me, so let's do it. What's the top one going to factor into? X plus 2x minus 2. What's the bottom going to factor into? X minus 5, x minus 5. So let's think about what x's we need to use. On the top, I need a negative 2 and a positive 2. On the bottom, I need just what? A 5. It doesn't matter that it happens twice. I'm just going to use it once. Okay? So we find all the zeros. Now let's go to our sign chart. Okay, it's everything except those values we just put. So I had a negative 2, a 2, and a 5. Now, one thing I will caution you against is what I call assume-aside. All right? We like to assume that things just switch. Okay? That is not always true. All right? So you really do need to test numbers. Okay? All right. Give me a number that's smaller than negative 2. Negative 3. And we're going to plug them into these parentheses. Okay? Never plug them into the original. Plug them into the parentheses. You can see the outcome better. Okay? So if I start with negative 3, that would give me a negative times a negative over a negative times a negative. Okay? What would my final sign be for that fraction? Positive. Good. Okay. Give me a number between negative 2 and 2. 0. Okay, let's plug that in. I'd get a positive and a negative, and then I'd get a negative and a negative. What's my overall sign going to be at the end? Negative. Between 2 and 5. Three, that'd be good. All right, so we plug that in. I'd get a positive and a positive, a negative and a negative. Okay. What would I end up with overall? Positive. Okay. And then something bigger than 5. A 6. Okay. So I'd get a positive over a positive, no. 6 plus 2 is positive. 6 minus 2 is positive. Yeah. And then I'd get a positive and a positive. So I end up with a positive. Okay. So there's one of the ones where it didn't switch. Okay. So you can't do this. Don't assume aside. Right. So this time I want to be less than 0. All right. Which pieces are we taking? Or piece? The negatives. Okay. Now, I didn't put this in to start, but let's talk about our parentheses. Where do I need parentheses? Which number gets the parentheses? The 5, okay? The 5 gets the parenthesis because it came from the bottom, okay? It came from the bottom, so it gets the parenthesis. So if I look, my only negative is between negative 2 and positive 2. Neither one of those have the parenthesis, so my solution, our bracket, negative 2, bracket, positive 2. And that's my solution. What do you think? All right, I want y'all to try the next one, just that next one. Right. And then check it with a friend. Be sure you agree. which means you have to do it, Wilmer. I'm picking on you. You set yourself up.
I started to draw that when she got to that question.
Yeah, but you can just look at what it says. No, just like look at it. Right here, like this down. Okay, so there's, because remember she said that only the users. She's so weird. She's so weird too. That's what I got, but I also have no idea what it is. I heard it, she told me right now. She said like, right now, the numerator, only has zeros or something. Like, only the numerator has zeros, and there's no zeros in the numerator, so we can just. Yes. Right. What if you first everything zero? No, you have to do a number less than 3. So it'd be 2, and 2 would be 3 negative. And then 4 minus 3 is positive.
All right, let's take a look at this one, okay? So can I factor the numerator? No, okay? Does 2 equal 0? No, okay? So the only number that I'm going to consider is coming from the denominator, which is a positive 3. Okay, so I do the opposite. So we're going to go to our number line, and the only thing I'm going to put it on is a 3. Do I need to put parentheses around that 3? Yes, okay, because it came from the denominator. All right, so now let's pick a number smaller than 3, 0. So 2, the top's going to always be positive, which is nice. 0 minus 3 would give me a negative, so that gives me a negative. And then on the other side, if I pick 4, the top's always positive. 4 minus 3 would be positive, and I get positive, okay? So I'm looking for where it's greater than 0. So is that going to be the positive or the negative pieces? Positive pieces. And so when we write our interval, okay, we're going to start at that negative 3, or that 3. It's got a parenthesis. It goes forever to the right because there's that arrow, so positive infinity. Okay? How'd you do? Okay, it's all right, it happens. Okay, Try the second one. You already did it, didn't you? We're ahead. Phew. How's track practice? I noticed y'all been outside. Okay. Yeah. Okay.
You said it will last me the whole day.
Well, it does for me.
You got your charger? You can sit over there.
You should have asked her, dude.
Wait, how much negatives? Oh, it is positive. It's okay, so it'd be -5 to be practice.
Oh, wait a minute. Helps if I do my arithmetic. -6. Yeah, I did that wrong. that better? Let me double check myself.
Because it's less than.
Well, you could just put -5 on brackets.
Yes, ma'am.
The parentheses on the top for smaller than -5 would be negative.
This is positive.
I put -6 in there.
This is positive.
Oh, yeah. Okay, I was right. I was just making sure. Like, my brain is having a, you know what?
I heard confusion.
Okay, so I was right to start with. Okay. I'm making sure.
So then it would be negative. To -2.
Okay. Phew. It's easy to confuse yourself, right? It's easy to confuse yourself. You gotta be careful. Okay, let's do one more. All right. But are you understanding the sign chart? That's the most important thing because that's so different than anything you've probably ever seen before. It's an organizational tool. We use it a lot.
Bro, your handwriting is
All right. Let's look at this one. Do I need to go back? Do I need to go back? Okay, just making sure. All right. All right, this one's factored for me. Yay, yay. Okay. So I get 1 and -2 on the top. And I get +2 on the bottom. All right. So -2, 1, and 2. All right. Do I need parentheses on any of these? The 2. Okay, because it came out of the denominator. And when we're looking at our inequality, we are doing greater than or equal to. So that means, you know, anything on the top is going to get a bracket. Okay. All right. So less than -2. Let me ask you a question. Does that second parenthesis on the top matter? This x plus 2, what's going to happen when I square it? It'll always be positive. So the only one that's really going to control anything is the first parenthesis. Okay, so you can skip plugging into the second parenthesis or you can plug it in and do what you need to do. Okay, it all works the same. Just trying to save you some time. So if I do -3, -3 minus 1 would be a negative. The second one's always positive. And the -3 minus 2 would be a negative. So I should get a positive. All right, between -2 and 1, 0. So I'd get a negative, always a positive, and a negative. So I get another positive. 1 to 2, we could use 1.5. That would give me a positive and a negative. And then I could use 3. So I get a positive, and a positive. So I get a positive. Okay. Okay, so now let's think about our solution. This is where we've got to be careful, okay? We want to be greater than equal to 0, so are we looking for positives or negatives? Positives. And I'm positive those first 2 sections and that last section, okay? Now, let's talk about how we write this, okay? Is there a parenthesis around that -2? No. Which means it can be part of the equal to. So I can just use one interval to cover that whole first 2 sections, okay? If there were parentheses around that -2, or if I did not have a bar under that inequality, I'd have to do them separate, okay? Because I could not include the -2, all right? But because it's equal to, we good. So we're going to go start over here on the left. So that would be -infinity, and we're good all the way to 1. And then we're going to pick up again. And I could put a bracket on 1, couldn't I? Yep. I can put a bracket on 1. And then I'm going to pick up again at +2 and go forever to the right. So positive infinity. So that's my solution. If you did practice anything tonight, practice the inequalities, okay? For sure, because they're just different, all right? Last one, I gave you a graph, okay? And we want to solve inequalities using the graph, okay? So f of x is that whole function right there. We're looking for where that whole function is above 0, okay? Highlighting works for me, so I'm going to start this one. We want to be less than or equal to 0, okay? So is that above or below the x-axis? Below, okay? So the only place I'm below the x-axis is that little piece right there and this little piece right here. Okay. Now, I can equal 0, so I'm going to include the numbers where it hits 0 as part of my answer. Okay. What x value does it start being underneath the graph or underneath the x-axis? -3. Okay. I can't include -3 because it's that asymptote there. Okay. And it stops when x becomes who? -1. That's a 0, so we're going to box that bad boy in. Okay. The next place it goes underneath the x-axis, it starts at 2. It's equal to 0 there, so I'm going to include 2. And it goes until x hits what? +3. Okay, so that's my solution on that piece. All right. Okay. Next one. We're looking for where this function is greater than 0, okay, where it's above the axis. Notice there's no equal to. So are we going to have any brackets anywhere? No, okay. I'm above the x-axis on this little swooshy piece, on this little bitty piece here at the axis, and this other swooshy piece, okay. So there's 3 pieces that I'm going to include, all right. It's all the way to the left, so we're going to start at -infinity. And that first swoosh stops when I get to what x value? -3. Okay. Then I get to my piece that's just above the x-axis, all right? That starts at -1. I'm not going to include it because there's no bar on my inequality. And it stops at 2. All right? And then that last piece is the swooshy piece over there, which starts at +3, and it goes for all my x's out to the right, so +infinity. So we had 3 different spots there where it was above the x-axis. Okay. All right. Last one. The nice thing about graphs is we can do some of those inequalities that are not around 0, okay, because they give me the picture. So for this one, I'm looking for where this graph is greater than or equal to 1. Okay? In other words, where is it above that purple line that I just drew? How many pieces is that? Just 2 pieces, okay? And those 2 pieces are right here in my little swooshes. Okay? So when I write those intervals, -infinity to that first asymptote, 3 to +infinity. Okay? So question about the graph part. All right. So there's 2 worksheets attached that were printed back there. Worksheet A for 1.7 and worksheet A for 1.8. Okay. So on the first one, 1, 3, 4, 5, 9, 11, 15. On the second one, 1, 3, 5, 7, 8, 9, 11, 13, 17, 19. Okay, that's more than I typically give, but it's just a good variety of all the stuff we talked about. Do what you need to do. Okay, and if you need more practice, there's more there. Okay, it's nowhere near the end of all that's available. Okay, you do have a wrap up today on Google Classroom. So if you'll get in there and get that done for me before you leave, we've got about 11 minutes. Okay, so should give you plenty of time to get that done. Good job today. All right, we're going to do new lessons the next 3 days, so. But it's a lot of information.